Electric potential. First of all, I'm going to define the electric potential in general. Its definition is like electrostatic, must say, potential at any point P is equal to the work done to bring a unit positive test charge Q naught at that point. It's actually a definition which is a thumb rule. It is applicable everywhere in electrostatics. Now, what this definition says, electrostatic potential at any point P, definitely in some electric field, is equal to the work done to bring a unit positive test charge Q naught. First of all, explain what this Q naught is. Q naught is a very small charge which can experience the electric field, the electric force, but it can't generate its own force. Like you can take it, suppose there is already a charge, a collection of charge of say 4 coulomb, and we bring a 1 microcoulomb charge or 1 millicoulomb charge. Then 1 micro or 1 millicoulomb compared to 4 coulomb is very small number. So in that case, this charge becomes a test charge. So practically saying, the charge in our consideration with respect to that Q naught has very small value, then it only experiences the effect of the other charge or charge collections. So it's called test charge. Now, what exactly is the work done to bring this test charge Q naught at that point? Now, the very important thing here, I write here as a note that electric potential is the property of a point. Electric potential is the property of a, actually, I haven't talked about any charge distribution, configuration, whatever. I have told only about the point P, the test charge Q naught. Right? It's very clear. Now, let's take a simple example. Let's derive it for a point charge. Electric potential V due to a point charge capital. Look, here is a capital Q charge placed at some position, say O. We want to find electric potential at this point P, which is at distance r from it. To find electric potential, that it is fixed. This plus Q is fixed. Now what we do, we are bringing a unit positive test charge from infinity to that point. That was important. To bring a unit test charge from infinity to that point. At any moment, suppose it is at this point B, suppose I take this point A, will be better. And this distance is x at that moment. This direction I am taking positive, this direction I am taking negative. Right? Now it is displaced a little BB dash. This distance BB dash is equal to dx. Suppose this I take x-axis, this is y-axis, then this direction is I cap and this is minus I cap. Because it's along one line, so we can easily assign positive and negative directions. Now, at this moment, when Q naught is at B, the force experienced by Q naught upon 4 pi epsilon x square I cap. Force will be in this direction, right? As it is displaced dx from right to left, I can write dx minus I cap. I hope you understand. Now, the work done from B to B dash dw f dot dx. Very simple. This is a scalar quantity. This is a scalar. The dot product occurs between the vectors only. The dot product will occur between I cap and minus I cap. So I have q naught dx by 4 pi epsilon x square I cap dot minus I cap. It is minus 1. I have this detail. Now I integrate as per the definition from infinity to r. Right? This work done is from infinity. This will be w is equal to q naught upon 4 pi epsilon naught as constant. Here is minus sign and integration is minus of 1 by x from infinity to r. For the new people, I can say x minus 2 dx is equal to x minus 2 plus 1 upon minus 2 plus 1. It is x minus 1 upon minus 1 minus of 1 upon x. Right? We have this minus minus becomes plus. W is equal to q naught 4 pi epsilon naught 1 by x 1 by r minus 1 by infinity. W is equal to q naught 4 pi epsilon naught r. As per the definition, the work done per unit charge W by q naught q by 4 pi epsilon naught r. This is called the potential. Q upon 4 pi epsilon naught r. This is potential at this point P. In plain words, we write K Q by R. Right? In this way, we have the definition of potential. Sometimes students ask me another question, which is related to the potential energy. Well, it is given as, let me explain it. There are 2 points A and B. Right? Here is potential VA, here is potential B. Now, better defining W work done is stored. You say this is positive charge, this is positive charge. You are bringing together. Then there is the repulsion. We are working externally. Now, if we leave them, they will move away. They will have kinetic energy. From where that kinetic energy comes? That kinetic energy comes from the potential energy. You are bringing them closer. Then potential energy of the system is increasing. Now, we leave them, they will move away. So, here the concern is that when we are doing work, that's being stored in the form of potential energy. I hope you understand. I hope you know this formula. F is equal to minus of du by dr and du equals to minus of f dr. Many times students ask me question. I simply write if potential energy as in this case, this charge q placed at point A, this P at q naught. Then I say the potential energy of the system is q naught upon 4 pi epsilon naught r. Now, there is a little misconception which students usually ask me. I will discuss here. What they asked, look, the work we calculated was q naught by 4 pi epsilon naught r. Now, student asked me, sir, we have delta u equals to minus of delta w or delta w minus of delta u. Here, delta u is what? U final minus u initial. U final is this q naught by r. Initial was 0. Then delta u becomes q naught by r. But here the work done is this. Now LHS of this equation is negative 2 q naught by r. I hope you are getting. We must have, if I place delta w here, I must get delta u. Delta u is what? uf minus ui. Potential energy is kq1 q2 by r. The final position is this one. Initial is infinity where the potential energy was 0. So change in potential energy is this, which is equals to minus of delta w. And delta w or simple w is this, which is a positive quantity. Now, if I write negative sign here, then I'm saying a positive quantity is equal to the negative quantity. Student asked me this question. Then I explained them in a fantastic way that this particular theorem is perfect in its place. But the work we have calculated, delta W, is by actually what we are doing. We are bringing the external agent, the external effort. At the same time, there was force, because some external agent will also have to exert force on the charge. Then it will come closer. At the same time, the electrostatic force is also working. And the process is quasi-static. It is taken very slow. The work is done by external agent, by us also. The work is done by the electrostatic force also simultaneously. Net sum of work must be 0, because there is no change in kinetic energy. Because as per the principle of work energy theorem, the net work done is equal to change in kinetic energy. Here I say delta W external plus delta W electrostatic, or I simply write W electrostatic must be 0. What we calculated is external. Then W electric is minus of W external. I write here. W external is Q naught by R. This is external. Then electric force work should be negative of it. And in this equation, now let me make it very clear. Potential energy minus delta W, the conservative force. Let me make you very clear. Listen. Potential energy is only defined in the influence of conservative force. Electrostatic force is conservative, so here the work done must be written by the electrostatic force, which is already negative. Then delta becomes minus of minus q naught by r, or I simply write delta u q naught by r. Got it? So it must be clear. Many times students ask me these questions are negative, positive. Keep in mind, here work done is by conservative force. I need to mention here. This particular relation is for the conservative forces. Work energy theorem is for all work done by all the forces. It must be very clear in class 11th. So here we have defined the potential energy and the potential. I simply say, if I have two charges, This is q1, this is q2. There is distance between them r. Now, at A potential is VA, at B potential is VB. VA minus VB, UA minus UB by Q naught. Or I simply say delta V, delta U by Q naught, or simply write Q. Delta U, Q delta V, or U equals to Q. The potential energy acquired by any charged particle placed in any field where the potential is V is Q into V, that's it. On this basis, there are lots of problems we will discuss now. There is another important point, the relation between E and V. Look, E is defined as Q upon 4 pi epsilon r square r cap, and at the same time V is defined as Q by 4 pi epsilon r. As I discussed, dW minus du, it is F dot dr, and this is du is Q dV. You can understand very easily now. I have given you just an example that U equals to QV, then du equals to Q dV. By this simple assessment, if I place Q here, it is minus d. F by Q is what? By the definition, electric field. E dot dr minus dV. Or I write here dV is equal to minus of E dot dr. This is integral relation. We can have the differential form also. We can have E is equal to minus of dV by dr. Now, if R is any point in space, R have x, y, z, all three components, right? Then this R is xi cap plus yj cap plus z. Then we need to use partial differentiation. Partial differentiation means this R has three variables x, y, z and z. Then partial differentiation means once you differentiate x keeping yz constant, next time you differentiate y keeping xz constant, and next to differentiate z keeping xy constant. Why it is done? Listen, it's very simple. Like differentiation, if I write del r upon del x, this is a symbol of it. I'll differentiate this keeping this and this constant. That means it's quite simple to reach at some point in 3D, at some point P. Suppose this distance is delta x, this distance is delta y, this distance is delta y. Then when I'm moving from O to A, then only x is changing, y z constant. If I am moving from A to B, then only y is changing, x and z are constant. From B to P, when I am moving, then z is changing and x and y are constant. It's so simple. Once you are making partial differentiation, del r upon del x, that means you are moving along x. And when you are moving along x-axis, definitely on the whole x-axis or any line parallel to x-axis, on that line y and z are definitely constant. So they must be treated as constants. Now when you move along y-axis, then only y is changing, x and z are constant. When moving along z-axis, then x and y are constant. Simple. It's not so It should not be, sometimes students think, okay, this is ridiculous kind of. No, it is not ridiculous. It has a logic. When you are moving in one direction, x, y, or z, then definitely rest two are constants. Now, for example, I write here, suppose I have any function x square y z square, then delta f by delta x, partial differentiation with respect to x. Then the function is traveled only along x, definitely y and z are constant. It is y z square. Differentiation of x is 2x. Similarly, del f by del y. Now I'll differentiate y keeping x and z constant. Differentiation of y with respect to y is 1. Del f upon del z. Keeping x and y constant, differentiating only z, it is 2z. Now the same thing is done in case of electric field and potential relation if it goes in 3 dimensions. Up here we have seen it is what it is, we have written E is equal to minus of dV by dr r cap. If r is equal to xi cap plus yj cap plus z cap. Now, what to do with this? In this situation, we'll simply write E is equal to minus of del v by del x I cap. Of course, when I'm moving along x-axis, then I'll write I cap del v upon del y j cap del v upon del z k cap. Now, very simple, I have Ex minus del v by del x, Ey minus del v by del y, Ez minus del v by del z. All these problems are solved. This is the relation between E and V. Now, we come to some potentials due to some charge arrangement, V due to electric dipole. First, of course, on the axis. Here I take minus q charge, here plus q charge, is point A, is point B, is point B. This distance is 2A, this distance is R. VP, V plus plus V minus. VP, due to this positive charge, KQ. This is Q, this is minus Q. Upon R minus A plus V minus K minus Q upon R plus. The VP is what? KQ common 1 by R minus A minus N comes from where? 1 upon R plus A. It is R square minus A square, R plus A minus R minus. I have finally this equation. Look here. It is what? VP KQ. R to R cancel, I have 2A. R square minus A square, it is approximately R square because R is far greater than A, then Q into 2A becomes P, and I have KP upon R square. This is potential of the axis of the dipole. It is Kp upon Rq. Direction, of course, no direction potential is a scalar quantity. Dot product of E and R is a scalar. Now, second one, on the equator. On the equator means this line. I hope you are very much familiar with this. This point is R, this point is R. This is 2A. And this is, I say, this is R and this is R dash. Then at point P, Vp is equal to Kq by R dash plus K minus Q by R dash Q. This same Vp Kq 1 by R dash minus 1 by R dash. It is what? 0. Now the equatorial line, the charges, both charges are at the same distance. From one charge there is positive potential, from the other charge there is negative potential, and potential is a scalar quantity. Positive plus negative becomes 0, magnitude are same. Now the last important derivation of potential for the dipole is very interesting. That is for any point r theta. Look, what is this? This is minus charge, this is plus charge. This point has, this is A, this is B. This point, from this point is center point O to P. This OP distance is R, right? Now this OP distance is R. Then to find the potentials between at point P due to the positive charge and negative charge. Look here, here it is a very clever calculation. This distance, this AP, this point is O. I extend this line. I draw a normal here. And for a moment I draw normal here. This point normal is suppose M, this point is N. This angle was theta, this is also theta. This total distance is 2A. So this distance is A, this point is O. Now here, this AM, this A, O, and this point M. Here I have drawn normal. This is theta. This is A. Now this distance, you can see clearly, before 90 is hypotenuse, before theta perpendicular, it is base. Now this distance is A cos theta. In the same way, this is theta. I have this NOB theta, this distance is A. This is 90. What is this distance? O, and it is again A cos theta. Look, AP is approximately equal to PM. PO. PM is PO plus OM. PO is R. OM is A cos theta. Then BP is actually PM. OP minus ON, or I simply write PO minus ON. PO is R, ON is what? A cos theta. This is P. Now, VP is equal to K minus Q upon AP plus K plus Q upon BP. Right? Now VP is equal to minus KQ upon AP. AP is what? R plus A cos theta plus KQ upon R minus A cos theta. I write positive sign first, then VP is KQ by R minus A cos theta minus KQ by R plus A cos theta. LCM R square minus A square cos square theta, and here I have KQ common, then here I have R plus A cos theta minus R minus A cos theta. Right? Finally, I have this situation that VP is what? KQ. R plus A cos theta minus R cancel. A cos theta plus A cos theta, it becomes 2A cos theta. R square minus A square cos square. A square cos square negligible to R square, it is R square. VP K Q into 2A cos of theta upon R square. Q into 2A KP cos theta by R square. Theta is the center. This is for any general point R theta. The electric potential due to a dipole. Now, I just introduced the concept of capacitor. Now, there is